Welcome to our video lecture on uncertainties and significant figures. Remember that you have a lecture outline available. If you want to use it, you can print it or annotate it as a PDF. If you just want to take notes your own way, you of course are more than welcome to take your notes your way. So our objectives for this video lecture, our goals are this. We are going to understand uncertainty. We'll talk about what that even means when it comes to measurement. We're going to learn how to express our quantities, our measurements, with significant figures, which I will usually refer to as sig figs because it's easier. And then we're also going to talk about lots of rules of sig figs. Definitely have ready your reference materials, so that front, back that you got in class, because those rules of significant figures are on those reference materials, and it would be easier to just annotate on that, because remember that you get to use those reference materials on every quiz and every test. All right. So before we get going, I do want you to think about the vocabulary that you already know. Things, ideas, concepts that are already in your head. We're going to use those and just take them a little bit further in this lecture. So uncertainty, significant, accuracy, precision, and place value. These are words that we use normally in the world. Today we're just going to talk about how they might be used specifically in chemistry. Quick place value review. Remember that the decimal here, when we go smaller, we have tenths, hundredths, thousandths, 10,000ths. So we throw those THs at the end. Getting bigger, we talk about the ones place, but sometimes we refer to the ones place as the units place. So keep that in mind. Units and ones are the same things. And then of course, tens, hundred thousands, 10,000. So we could go bigger, hundred thousands, millions, etc., etc. So thinking about place value, we're going to use that a lot when we get to the rules of sig figs. So first, we're coming to this idea of uncertainty, not knowing for certain something. And when it comes to measurement, sometimes we don't know for certain how much stuff we've got. So I'm looking at my beaker here. Notice that I have a count up: 100, 200, 300, 400. We also have a count down: 100, 200, 300, 400. And what's nice about having our numbers that both go up and down is this. I can fill up my beaker with some stuff and then I can measure the volume, but I could also fill up my beaker, pour some out, and measure down. We're going to go with the first method. We're going to assume that my beaker was empty and I added stuff, and so I'm going to measure from the bottom up. And I want to know about how much liquid do I have in this beaker. There's 100, 150, 200. There's my 250 line, my 300 line. So maybe we could say that I've got, like, if that's 200 and that's 250, maybe there's like 220 milliliters of liquid in the beaker. But could I also say there's like 216 milliliters? Would that be wrong or more right? 210? 225. Could any of those be possible? Can I really just kind of say it's somewhere between 200 and 250, 220, 225-ish? Is probably pretty close to as good as we're going to know because of the degree of uncertainty in this beaker. So uncertainty comes into play when we don't know exactly how much stuff we've got in our sample, but we can get pretty close. So when we're noting uncertainty, when we're writing uncertainty, our certain digits, I know for sure 17, and then I'm going to guess like a 0.6. In the last slide we were guessing at 20 or 16. And then I'm going to show how much wiggle room my guess has. And so I'm going to say plus or minus 0.1 of a kilogram. So 17.6 plus or minus 0.1 of a kilogram is telling me that it could be 17.6, or it could be a tenth of a kilogram more, maybe up to 17.7. Or maybe it could be 0.1 less, that minus, it could be 17.5. But it's definitely somewhere in between there, close to 17.6, but somewhere between 17.5 and 17.7. This is our uncertainty in science. So we've got our certain digits. We know for sure 17. This is the one that we guessed. and then we're going to show the wiggle room around our guess. Let's practice this one. So I've got 20, 30, 40. Here's my line for 50. I know for sure 40. It's not quite 50. I'm going to say 48. To figure out our plus or minus with measuring devices that we consider to be analog. Analog, we're using our eyes. There's not a digital reading of the volume. So we're using our eyes to determine. What we're going to do is either cut our graduations in half. So if this is 50 and this is 40, 40 to 50 is 10. I'm going to take that 10, I'm going to cut it in half. That's going to be 5. So I'm going to say 48. I know for sure the 4. I'm guessing the 8. I'm going to say plus or minus 5 because half of these guys, 40 to 50, half of 10 is 5. So 48 plus or minus 5 milliliters. Sometimes, you need to check your glassware, sometimes it'll give you at the top of the glassware a plus or minus 5% or 10% or 2%. And then you could say instead of 48 plus or minus 5 milliliters, it could be plus or minus 5% of those milliliters. Check your glassware so you know for sure. Let's talk about what's certain. Our certain digit is the 4. I know for sure it's 40 something. Our uncertain digit is going to be that 8. That's the one I guessed. And then our degree of uncertainty plus or minus 5, again, because I'm going to figure out what's my increment. 40 to 50 is 10. Chop that 10 in half is 5. 48 plus or minus 5. Let's look at this one. So same idea. I see this is my line. Oh, let me get a better color. This is my line for 6. I don't know if that's better. Let me try again. Here's, yeah, that's better. Here's my line for 8, which means that this line in the middle is my 7. And I've got 1, 2, 3, 4, 5 lines between. So each one of these is a 0.2. So 6.0 on this line. 6.2, 6.4, 6.6, 6.8. So when we're reading the volume of liquid in a graduated cylinder, we're going to measure using the meniscus. So the meniscus is this curvy little piece of the water. It's because water is polar. We'll talk a lot about water being polar later on in the school year, but we're going to measure from the bottom of the meniscus. So it looks to me like it's 6.6, but maybe just a tiny little bit above. So I'm going to say 6.61 is my guess. Certain, certain, uncertain digit, that's the guess that I made. I'm going to do plus or minus. Remember, again, we're going to look at our graduations. Each one of our graduations or our lines, our increments, is 0.2. 0.6 to 0.8 to 7 to 7.2 to 7.4. So each one of these is 0.2. We're going to divide that by 2. And so we're going to have a plus or minus 0.2 divided by 2 is 0.1. 0.1. But here's a quirky thing. Since that's in the 10th place, I also need this guy to be in the 10th place. So our volume is going to be 6.61 plus or minus 0.10 milliliters. Let's look at this one. 35, 40. So each of these lines is 1. 36, 37, 38, 39. Measure from the bottom of the meniscus. So I'm going with 36 for sure, 0.5. 36.5 I think is pretty reasonable. Plus or minus, remember that we're going to, with these analog measuring devices, we're going to figure out what's our increment. Each increment is 1 milliliter. We're going to divide it in 2. That's going to be half a milliliter. So 36.5 plus or minus 0.5 milliliters is going to be our volume. So when we're measuring things, we like to describe groups of measurement, our data, as being accurate and or precise. Accuracy and precision in regular vocabulary are sometimes the same things. For us in chemistry, they're a little bit different. So accuracy is how close a value is to what it's supposed to be, its actual or its accepted value. For example, if the density of silver is 11.5, that's its accepted, its actual density, the real density of silver. And you do some math and you're like, ooh, I found that it's 11.47. Ooh, those are pretty close. Your value is accurate. What if you found the density of silver to be like 4.3? Whoa, not very close, not accurate at all. So again, we're going to take our actual, our accepted, the real value of something, compare our data to that. If it's close, then it's accurate. If it's not close, it's not accurate. Precision, now we're going to have a group of data and we're looking at how close the measurements in the data are to each other, not necessarily to the accepted value, simply to each other. So let's say, again, that I'm measuring my density of silver, and let's say that I get like 4.3, and then 4.2, and then 4.2, and then 4.4. Well, these are all super close to each other, so I would say that my data are precise. There's a lot of precision there, but definitely not accurate if my accepted value is still that 11.5. I can look at accuracy and precision visually with these targets. So notice here, I've got all of my data all here right at the bullseye. It is both accurate and precise. It's right on target, it's accurate, and it's all clumped tightly together, it's precise. This data is not on target, so the accuracy is quite low. However, because the data are very close to each other, the precision is high. If we look at this, we're pretty close to the bullseye, so we've got some good accuracy, but the pieces of data are not close to each other, so precision is low. Here, things are wackadoodle all over the place. We have neither accuracy nor precision. So thinking about accuracy and precision, which of these two measuring devices, we've got a beaker over here, we've got a graduated cylinder over here, which one do you think is going to be more accurate? Which one's going to be more precise? Which one's going to give you values that are closer to the real values? Which one's going to give you and your friends, if you're using the same device, a pretty similar number over and over and over? And hopefully you have already determined that graduated cylinders are way better than beakers when it comes to accuracy and precision of measuring the volume of liquids. So here is some data from an investigation into the density of aluminum. So in the first trial, we found that the density of aluminum was 3.4 grams per cubic centimeter, and then 3.3, and then 3.4. The accepted, the real, the actual density of aluminum is 2.7 grams per cubic centimeter. What do we think about this data? Is the data accurate? Is it precise? Neither? Both? Hopefully you're thinking the accuracy is pretty far off. 3.4 to 2.7, that's a pretty big difference. So not accurate. However, these pieces of data are pretty close to each other. So precision is a yes. So we have low accuracy, high precision. Those pieces of data are close to each other, but not close to the actual target. All right, so we're going to look at uncertainty one more time, and then we're going to start applying our rules of sig figs to our uncertainties. So here we have a graduated cylinder, 60 and 70, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of these pieces, each one of these increments is 1 milliliter. Half of that would be that 0.5 milliliters. So we're making a guess that we've got 60, 1, 2, 3.5. 63.5 plus or minus 0.5 milliliters. And again, all of these digits, my certain and my uncertain digit, all of them are considered significant. They're all important to my measurement. So even though the first two are certain and the last one is uncertain, all of them are significant. All of them matter when it comes to me thinking about my data. I'm not going to worry about my plus or minus when I'm counting significant figures. I'm just looking at my certain digits and my one uncertain digit. All right, so these are those rules for significant figures. These are in your reference materials that you got in class. So if you have those handy, you can definitely annotate as we go through. Sometimes it's just nice to have those nearby so that you can refer to them as we're talking. So rules for significant figures, non-zero digits. Non-zero digits are everything that isn't 0, 1 through 9, but not 0. So non-zero digits and then zeros between non-zeros. Zeros between non-zero digits are always significant. They always count. And we're going to talk about counting sig figs in the next couple slides. Leading zeros are not significant. Leading zeros are the ones that are just like placeholders. So all of these guys, they're just placeholders. They're leading zeros. They are not significant. Zeros to the right of non-zero digits. So I've got my non-zero digits. I have zeros to the right. They're only significant if there's a decimal place. So if I take that decimal place away, those zeros don't count. But if I put that decimal place back, those zeros do count. So zeros to the right of non-zero digits are significant if there's a decimal. For values written in scientific notation, like 1.2 times 10 to the 4th power, all of the digits in the coefficient are significant. This is the coefficient. And then in a common log, don't even worry about that. We won't talk about common logs until the second semester. All right, so let's practice using these rules to figure out how many sig figs are even in each of these pieces of data. So here I have 45,000 kilometers. Non-zero digits always count. So 4 and 5 are definitely going to count. So there's 1, 2 sig figs. How about these zeros? Do they count? Are they between non-zero digits? Nope, they're to the right. Zeros to the right are significant if there's a decimal. Is there a decimal? No. And so none of these zeros count. So 45,000 has only 2 sig figs. Basically, we're saying there's about 45,000 kilometers. There could be like 45,107. There could be 45,009. There's about 45,000, but maybe not exactly. So those zeros don't count. These guys are the only 2 significant digits. How about 45,001 kilometer? Well, non-zero digits, so still if 4 and 5 are going to count, our 1's going to count because it's also not a 0. Zeros between non-zero digits are significant. And so because these zeros are between numbers that are not 0, they do count. So this guy has 5 significant digits. All of these numbers are significant in this measurement because of that 1. The zeros are significant because they're between non-zero digits. Let's look at this one, 0.0000402 grams. So we know that the 4 and the 2 are going to count because they're not zeros. These guys are all leading zeros, and leading zeros are not significant. So these guys don't count. How about this one, 0? It's between non-zero digits, so it does count. We have 1, 2, 3 sig figs in this piece of data. How about this one? Again, I've got all of these zeros in the front that are simply holding that 4 in the correct place value. These guys are leading zeros, they don't count. That 2 is going to count because it's not a 0. This 0 is between, so it's going to count. What about this 0? Count, not count. It's a 0 to the right of a non-zero digit. Significant only if there's a decimal point. Is there a decimal point? There sure is. It's way up there, but it's still there. And so this guy does count. So our significant digits are 4020. There are 4 sig figs in this number. All right, so here's some more to practice. I would love for you to pause the video if you're feeling like you got this, and then restart the video and check your answers against the work that I'm going to do. If you're still not quite there, go ahead and keep listening. I'm going to talk through the answers. Get ready, get set. Here we go. All right, so 5's a non-zero, of course it's going to count. These guys are to the right of non-zero digits. There is a decimal, and so these guys all count. We have 3 sig figs, 5.00 milliliters, 3 sig figs. Over here, got that 5. I've got those 2 zeros again. There's no decimal, which means that these guys do not count. There's only 1 sig fig in this piece of data. Decimal, they count. No decimal, they don't count. No decimal. Guess what happens to those zeros? They don't count. Only the 1 is significant. There's 1 sig fig here. How about this one? 100. 100. It's like it's the same number, except there's a decimal. And so zeros to the right of all non-zero digits are significant. If there's a decimal, we have a decimal. These guys are significant. There's 3 sig figs. The difference here, 100 to 100, this one is saying rounded to 100. Could be like 80 or 90 or 107, and we just rounded to 100. This one is saying, no, we didn't round. It's like 100 point. And so maybe we rounded like 100.1, or maybe it was like 99.9, and we rounded to 100 to that ones place, that units place. Whereas over here, it could be anything from like 149 down to 50. This would all round to about 100. So that's why this is only 1 sig fig, and this is 3. This one has a whole lot more precision and accuracy than does this guy. Accurate and precise, not accurate and precise. Lots of rounding, not as much rounding. All right, let's look at these guys that are in scientific notation. We're going to count all the digits in the coefficient. Remember, this is our coefficient. 1, 2, 3, 4. 4 sig figs in this piece of data. This piece of data, I've got a 5. It doesn't matter that there's 36 zeros. Only that 5 is going to count. This guy only has 1 sig fig. All right, so the reason that we start counting sig figs is so that we can do math. When we are multiplying and dividing data, we're going to count how many sig figs are in each piece of data. Then we're going to round our final answer to the smaller number of sig figs. For example, let's say that I and a student were going to measure a garden plot. And I'm super lazy and I'm like, I don't know, I think it's like 2 meters. And then my student was like, I'm going to get out my calipers and my meter stick, and I find that the length is 3.782 meters. Super, super precise. Lots of energy put into getting a good measurement. Meanwhile, Lens was like, 2 meters. So when we multiply these two guys, 2 times 3.782 to find the area, the calculated number is 7.564 meters squared, which has a lot of decimal places, which is implying that we know pretty darn well just how big that area is. But we don't actually know the area that well, because Lens was like, I don't know, it was like 2 meters. And so we're going to round our final answer to the number of sig figs in this piece of data. If this is only significant to 1 digit, my answer can also only be significant to that same 1 digit. Otherwise, I'm exaggerating how good my answer is. So this guy, let me erase some of my scratches here. So since that 2 has only 1 sig fig, this guy has 4 sig figs. I'm going to look for the smaller number of sig figs. 1 is smaller than 4. And so my final answer can have only 1 sig fig. So I'm going to take my 7.564 and I'm going to round it to only 1 sig fig. I'm going to keep the 7, except I'm going to round. So I'm going to look at the next digit over that 5. It's going to make that 7 round up to an 8. So my final answer is actually going to be 8 squared meters, which makes sense because if my length is only about 2-ish, then my area should be only about 8-ish, not 7.564. That's way too much precision and accuracy given how sketchy that measurement was. All right, let's practice another one. So here, I'm going to skip ahead a little bit. I'm going to go ahead and give you the calculated answers. We're just going to practice looking at the numbers of sig figs. So I'm going to do one together, and then I'm going to have you pause the video, and you're going to do the last 2 on your own. So I'm going to, again, when we multiply and divide, we're going to count the number of sig figs in each piece of data. This guy has 2 sig figs. This guy, remember that zeros between non-zero digits do count. So this one has 3 sig figs. I'm going to find the smaller number of sig figs. 2 is less than 3, so 2 is my smaller number. I can only keep 2 sig figs in my final answer. I'm going to keep a 1 and I'm going to keep a 2, but that 5 is going to turn that 2 into a 3. My final answer is 13 centimeters squared. I get to keep 1, 2 sig figs. All right, go ahead and pause the video, look at these answers, and then just round the answers to the correct number of sig figs. When you're ready, start playing the video again to check your answers. All right, hopefully you have some answers. We've got 1, 2, 3 sig figs here. I've got only 1 sig fig here. That 0 doesn't count because there's no decimal place. 1 is less than 3, and so I'm going to keep 1 sig fig in my final answer. We're going to keep that 1, but that 7 is going to round that 1 up to a 2. 2 hours is my final answer with the correct number of sig figs. Remember that when we're working with scientific notation, all of the digits in the coefficient count. So here's 3 and here's 2. Final answer gets to keep 2 because 2 is less than 3. So I'm going to keep that 2 and that 0. That 4 is not going to round that 0 up. It's going to stay at a 0. Remember that 5 and up will round up. Less than 5, we're going to stay where we are. And so our final answer is going to keep those 2 sig figs 2.0. Crazy important thing when we're working with scientific notation, do not forget your exponent. So it's going to be 2, and you can write E12 meters, or you can do 2 times 10 to the 12th meters. Good? Don't lose your exponents. All right. Adding and subtraction, I think, are harder. So different set of rules when we add and subtract. What we're going to do is we're going to look at the place value. That's why I had that place value chart way back at the start of this lecture. So we're going to look at the place value of the last significant figure in each piece of data, and then we're going to round the final answer to the largest, which doesn't make any sense until we practice it. So I'm going to look at the place value of the last sig fig. So looking at this, the last sig fig is a 5, and it's in the tenths, hundredths, thousandths place. Looking at this piece of data, I have a 2 in the last significant digit, and that's in the tenths, hundredths place. So now I need to figure out what's bigger, hundredths or thousandths. Remember, we're working with decimals, things go backwards. And so a hundredth is actually larger than a thousandth, because if I take a cake and I chop it into 100 pieces, those pieces are bigger than if I chop the same cake into 1,000 pieces. So hundreds are larger than thousands, and so I'm going to round my final answer to the largest place value to the hundredths place. So I see decimal place, tenths place, hundredths place. Hundredths place is here. The 5 in the thousandths place is going to round that 5 up to a 6. And so my final answer is going to be 12.86. This 5 rounds this 5 in the hundredths place up to a 6. 12.86 meters is my answer. All right, just like we did with the previous practice chunk, I'm going to do the first one with you. You're going to pause the video, do the next 2 on your own, and then check your work. All right, get ready, get set. I'm going to look at my last sig fig. Here it's in the tenths place. I'm going to look at my last sig fig here. It's in the tenths, hundredths, thousandths place. What's bigger, tenths or thousandths? Tenths is bigger. We're going to round to the tenths place, which is right here in my answer. That 0 is not going to change that 5. My final answer is going to be 11.5 grams. All right, pause the video, do the next 2, restart the video, and check your work. All right, hopefully you're ready. This one, my friends, is crazy sauce, blow your mind. So we're going to add up all these pieces of data. We get 220.3 milliliters. Final decimal place is in the tenths. Whoa, if I could spell tenths. Final decimal place is in the units. Are you ready? The final decimal, or the final sig fig, the last sig fig, is actually that 2. There's no decimal, and so these zeros don't count. Hundreds place is the place value of the last sig fig, the only sig fig in that piece of data. The largest is the hundreds place, which means that in our final answer, we are going to round to the hundreds place. That 2 is going to leave that 2 as 2. The final answer is 200 milliliters, but that doesn't make any sense. How can I start with 200 and add 15 and add 5.3 and still have only 200? Well, it's because, remember that this 200 is 200-ish. It's like, yeah, we could have anything between 150 and 249, and those both round to 200. And so we could totally have 180 and add some stuff and still have only about 200. So it's because this is not exactly 200. It's 200-ish. All right, one more. Last place value is in the tenths, hundredths, thousandths place. Tenths, hundredths, thousandths, 10,000ths place. What's bigger? Well, 1,000 is bigger than 10,000, and so we're going to round to the thousandth place. Tenths, hundredths, thousandths. That 4 is going to leave that 7 right where it is. So our final answer is going to be 23.997 MOL for moles is our final answer when we do our sig fig check. All right. So let's check to make sure that we accomplish all the objectives of this lecture. Do we understand uncertainty? Hopefully we understand it better. We're going to practice in class, so don't panic if you're still kind of uncertain about uncertainty. See what I did there? All right, can we express quantities with sig figs and uncertainty like 12.1 plus or minus 0.5? There's our uncertainty. We know that these are certain digits and this is uncertain, but all of those are significant. Our rules of sig figs, they're on our reference materials. Use those, refer to them. They're super helpful to have on paper. Good work today, my friends. See you in class.